Can you hear me?
Now
Now
this
you are
third.
audible?
You are audible. Louder, please.
Now echo is not coming
Just
right.
down the speakers.
No, no.
No echo.
Okay.
No, echo, no. See, now when you speak, now start. Just don't put on any mic.
We are live now.
See, your office is coming up from here.
Now when Kalana will be talking, how it will say to you? You are there, no?
I'm just sitting.
Yeah. After we Kalana
How
will
many?
be talking.
I'm taking this.
Hello everyone. A pleasant good morning to one and all here. My name is Vaishali Parkhi. I am Assistant Professor, Mathematics, Department of Science and Humanities of Don Bosco College of Engineering, Patoda, Goa. It is my honor to welcome you all in this webinar on mathematical modeling and number theory. First, I would like to thank our director, Reverend Father Kinle de Cruz, Principal Dr. Nina Panandikar, and Registrar and HOD, Head of the Department of Science and Humanities Department, Dr. Kala Nayak, for providing such a wonderful opportunity and being our backbone for all events. I also thank Professor Gladys De Silva, R&D Coordinator of Science and Humanities Department, for all her support. I extend my warm welcome to our beloved Head of the Department, Dr. Kala Nayak, to share her views. Over to you, ma'am.
Thank you, Vaishali. Welcome to the exciting world of mathematics. Every year, India celebrates National Mathematics Day on December 22nd to commemorate the birth anniversary of mathematician Srinivasa Ramanujan. He had a wealth of ideas that can transform and reshape mathematics. The main objective behind the celebration of National Mathematics Day is to make people aware of the development of mathematics and its importance in the growth of humanity. The message of the 2020 theme is that mathematics is everywhere. Needless to say, mathematics is a part of the cultural heritage of humanity, essential to technological advancement while being a tool for development. With this motive in mind, the Department of Science and Humanities, in association with the Research and Development Cell of Don Bosco College of Engineering, Patoda, Goa, is organizing Time Mind, a web series. The first topic under this series is mathematical modeling and number theory. As the head of the department, I, Dr. Kala Nayak, welcome the speakers, Dr. C. Venugopal, Professor in Mathematics at Sri Sathya Sai University of Human Excellence, Kalburgi, Karnataka, and Dr. Himandri Mukherjee, Assistant Professor in Mathematics at BIT Pilani, Goa campus. A warm welcome to the participants who have shown keen interest and registered for this first web series. We are hopeful that Dr. Ramanujan's work will continue to inspire mathematicians and science enthusiasts present today. Thank you for giving me opportunity, Vaishali. Over to you.
Amit, shift to you. Thank you, ma'am, for your kind words and motivating words. Fragrance of flowers spreads only in the direction of wind, but goodness of a person spreads in all directions. Today, we have with us such an inspirational personality who is highly passionate about delivering the best to the participants. Dr. T. Venugopal. He is currently a professor of mathematics in Department of Mathematics and Computer Science of Sri Satya Sai University, Karnataka. He was the best outgoing PG student of St. Xavier's College and CSIR UGC Junior and Senior Research Fellow at Madurai Kamraj University. He has university level UG and PG teaching experience, administrative experience as head, chief warden, director, dean and controller of examinations over 25 years. He has given nearly 100 talks, webinars, hands-on workshops on teaching mathematics in schools, college level mathematics with software and on spirituality also. He has so far guided 10 PhD students and 21 MPhil scholars and has over 50 publications to his credits. We are really honored to have you today, sir. Sir, kindly take over the session.
Yeah. Yes, madam. So, shall we start then?
Yes. Yes.
I am hearing my voice again. Yes. Let me start my presentation. I am hearing my voice again. Some speaker is on at your end. Don't you hear me twice? You are hearing me twice. Some mic is on or some speaker is on at your end, which is resulting in echo. Yes.
Sir, we can hear you very clearly, but
That's right. I will start now.
yes, sir.
Yes. Starting my presentation. This is Professor Venugopal. I am Professor of Mathematics in the Department of Mathematics and Computer Science of Sri Satya Sai University of Human Excellence, Gulbarga. This group of institutions under Satya Sai Lokabandha Trust, they offer completely free education in over 30 schools in university and PU colleges. I am proud to be part of that. Thanks to my university for permitting me to get into this. And this is a brief contact details, my contact details. I think only few are in Google Meet and some I could see some on YouTube. They can get in touch with me through this WhatsApp details or email, or they are welcome to get into my channel to see the videos over there. If doubts are there, they can WhatsApp or they can put in the chat box. Okay. So this is a talk arranged by Don Bosco College of Engineering, Baroda, Goa. I am very thankful to the organizers of the Department of Mathematics of Don Bosco College of Engineering, Goa. I have visited there earlier, maybe some years ago. I was there to attend some 5-day workshop on statistical modeling or something. very nice reception was there, very nice program was there. So glad to be with you again. So this will be an appetizer to mathematical modeling in real life situations with a special reference to optimization problems. In fact, functional optimization, I will get into business optimization of engineering problem and others also. Thanks to the organizers again. So this concept of mathematical modeling is found in many books. Okay. So I am responsible for the flow. The contents I have taken from various books with acknowledgements. Some templates I am using with due acknowledgement to those books. What will be covered in this talk? What can you expect from me? Maybe for the next, next 1.5 hours or so. This talk will give an exposure to mathematical modeling. I assume that people are new, or you already know, find out whether something new over here. And if you wish, I can send certain exercises after this webinar so that you can get onto it. So let me get into this. Mathematical modeling of real world problems. When we say real world problems, there are many from elementary to very advanced. You can see mathematics in launching of rockets also. It is sitting there. Still, we will start with something elementary. Okay? But the max guys are always like me. You see the professor over there trying using a chair over there to draw a straight line. So mathematical modeling is a language. Mathematics is the modeling language of real world problem. There's a warning is there always with mathematics. Yeah, beginning, yeah, mistake made in the beginning may take a lifetime to correct. You will have to be very careful in modeling. A brief telling of what are the other models sitting in this world. This iconic model, schematic, descriptive, prescriptive, predictive, normatic, static, dynamic, analytic, simulative models, deterministic, stochastic, probabilistic, economical, biological. All these models are there. We will concentrate on mathematical modeling, which is algorithmic and logical. What's a model? A model is a schematic description of a system. There are two types of models, concrete and abstract. Mathematical models are abstract. Okay. This, since this engineering college that I'm addressing, I understand my MSc students are also there. Engineering and science students heavily on mathematical modeling, whether they are aware of it or not. I will dig into that. And people may think computers are doing everything. Okay, why do you need this concept of modeling on paper, right? See, however good the computation may be, it is highly risky to abstract computer calculations as it is without having done some parallel closed form modeling to benchmark the computer results. That's what you always do, right? If you write a very simple C programming, you first check it with known numbers. Maybe if it is to add 10 numbers, you first add 10 numbers in your calculator and check whether the model works correctly. Then only you can expand it. So without benchmarking and validation, we cannot be sure whether the computer talks sense. Okay, computer program is always there. If there is a bug in the program, it will result in some result which doesn't make sense. So mathematical modeling helps you to benchmark and validate the model on hand. So model is a cognitive activity. right? That's and modeling activity can be done in several languages. That's what we do in various forms. Yes, light flow chart is there. Just have a look at it. I won't get detailed into that. So when do you see? Usually the thing is in mathematical modeling, you take a real world problem, you abstract it, shape it in the form of equations and all that, get into the world of mathematics, use the tools available in mathematics, solve them, and get the result out of it, interpret the results in terms of the real world problem so that the others can follow that. This is the general structure. And I follow a book and I have taken certain topics from it. There are experimental modeling is there, simulation modeling. Simulation modeling I will be touching. Okay. Then probabilistic modeling is there. Maybe in queuing theory we can touch it, or simulation models we use probabilities. I will concentrate more on this linear programming models, business optimization models related to somewhat engineering problems and the business optimization problems. Of course, there are other models. Differential equation modeling is there. I will just highlight it. Okay. And systems of differential equations, continuous optimization models, and graphs as models. These are the broad categories that are there. I will touch upon many and concentrate on. So let me start with a very simple example for the benefit of those who are wondering what this mathematical modeling is. It is not new to you. It's not new to you. We have been doing it from school days. See, if we take a very, very simple problem, the length and width of a rectangle together measure 130 yards. The difference is 8 yards. What's the area of the rectangle? These are the so-called word problems in school mathematics. Now, this will result in a mathematical model. There are two ways of solving this problem. First method requires a linear equation with one variable. Second method requires a system of equations with two variables. So when you get into equations, that means you are modeling there. And using the tools of mathematics to solve the model and get back to your problem. Okay. Just have a look at it. It's elementary only. The length of a rectangle, let it be x. Then width of the rectangle is x plus 8 as the difference is 8. Together they measure 130 yards. Then 2x plus 8 is 130. That means x is 61. That means the width is 69 and the area is 4209. This is one approach. See, here we are doing this 2x plus 8 equal to 130. That's I can call it a model if you permit me. So I will call it a model. And you are solving it to 2x equal to 130 to x equal to 61 using the tools of mathematics, a elementary tool in mathematics, division, right? So if I go to some other method, see maybe I say x is the length and y is the width, then x plus y is 130, x minus y is 8, and I get x is equal to 61, and I get the what's the area of the rectangle is 4209. So what do we do here? A word problem was given, rectangle. Maybe I can put it in a diagram. Then what do? I come back to the put it in terms of x and y. Then only a max guy can do that. This x plus y, x minus y. I am manipulating with that and getting x and y. Then I will say what is x, what is y in terms of the real. I will say, see here x is 61. There I say length is 61. Here I say y is 69. There I say breadth is 16. Something like that. Okay. Now this is a very, very simple example. Let us have a look at differential equation modeling. See, you know, for a falling stone, the only thing that pulls is the gravity. So that means the acceleration is gravity. That means y double dash is g. Okay. These diagrams I have taken from Advanced Engineering Mathematics by Chris. And for a parachutist, I have the differential equation mw dash equal to mg minus bv square. Okay, that depends on velocity, and there can be a differential equation to measure the water level, and the springs can be modeled mathematically. You get into differential. What do we do? You take maybe a circuit this side. You take a circuit, then convert it into a second order differential equation, Li double dash plus Ri dash 1 by Ci equal to E dash. Okay, then you get back to the world of differential equation, solve it using the methods available for differential equation, get the solution, and come back to the circuit to tell what current is there or not. Okay, few more differential equation modeling. I am brief on that, I know. Then about beams, the deformation of a beam, a pendulum, and the predator prey model, and all that. For that is a simultaneous differential equation, the last one. Okay, that's a very famous social modeling, right? Now let me touch upon algebraic modeling. Okay, I will tell you how this maybe this expressions, algebraic expressions, how do they help you to design a circuit? I will be brief on that again. There's a very beautiful book on that, applied abstract algebra by Liddell and Pills. Liddell and Pills. I will be brief on that again. I see in so very elementary problem in fast printers for computers with high speed paper transport, careful control of paper movement is essential. We draw a schematic model of the method of paper transportation to control mechanism. The motor operates with a pair of cylinders. I will show the diagram, which transports the paper strip. The paper strip forms a light barrier between a lamp and this what's a machine, and this when the paper is out of when the machine is out of paper, that means the some sensor receives light because paper barrier is not there, that will switch off the motor. We might have seen in all printed, paper is not there, it won't print, it won't print on the drum. Okay, now let us model this, let us model this. See, just have a look at the diagram. This is the diagram. This is a warning lamp, and a photo cell is there to sense the light, and a lamp is there, and the paper is in between. Paper strip, it forms a barrier. It forms a barrier between the photo cell and the lamp. When the paper is out there, the lamp, the photo cell will sense the lamp, and it will switch off the motor. Right. Now, let us put some numbers over here. We will say assign a number A for brightness. So when this A comes, mathematics gets it. And we will say a minimum brightness is there. Minimum brightness is there. Then what we do, we assign some numbers. We assign some numbers with A and B. If brightness is greater than A1 is 1. If brightness is less than A1 is 0. I am assigning certain numbers there. If brightness is greater than B, the minimum threshold, then A2 is 1. If it is less than B, A2 is 0. A3 is 1 if paper strip is broken. A3 is 0 if paper strip is unbroken. In that case, B will be less than A. Then we will have a function on triplet A1, A2, A3. That triplet will be 1 if motor operates. If the triplet is 0, motor is switched off. If the triplet is 1, warning lamp will start operating, and for a second function. If for a second function, if it is 0, the warning lamp does not operate. Right. Now, let's form a very simple truth table kind of thing. There are various combinations of this A1, A2, A3. What are this A1, A2, A3? Brightness and the minimum brightness, and about the status of paper strip, and two possibilities are not possible. Two possibilities are ruled out, they are cancelled. Out of the other 6 possibilities, we are writing the summary of those functions. So when the summary of those functions, we get into a disjunctive normal form. That's a kind of arithmetic expression, x1, x2, x3 dash plus x1, x2, x3 dash, which can be simplified with the laws of Boolean algebra as x2, x3 dash, and the P2 is written as x1, x dash, x1 dash, x2. Very simple, this is a variable. So with that variable, I am converting it into a switching circuit. See, the switching circuit is seen there. So the model here that is shown here, okay, I'm not getting into details. I'm not working it out. I'm just trying to impress upon you that a printer can be modeled mathematically with polynomial expressions, which can be simplified with Boolean algebra laws, that can result in a simplified switching circuit. Okay, and that will help us to frame the circuit for that. What is that? The printer, which is supposed to switch off, which is supposed not to print when it is out of paper. Okay, so let me get into a very basic form of modeling that the school students come across other than the simultaneous equations. Modeling with matrices. A matrix is a very good example of modeling. Matrix is a very good example of mathematical modeling. Where it is applied, though simple, it's applied in scientific computing libraries. They have seats in matrix calculus. The matrix maximum principle uses non-negative matrices. Control theory in engineering involves spectral analysis of matrices. The DFT, discrete Fourier transformation, makes use of Toeplitz matrices. Statistics is based on correlation matrices. Symmetric matrices appear in continuum mechanics. Markov processes need stochastic matrices. Graphs are usually represented as square matrices with adjacency matrix and all. And if coming to science, this quantum chemistry and quantum mechanics get into matrices. So matrices are always there. Now, for the benefit of maybe students may be there, a small example which results in a matrix calculation. Okay? There are three girl students with final grades. We know their averages for test projects, homeworks. We know their tests are 40% of the grade, projects are 50% of the grade, homework is 25% of the grade, and quizzes are 20% of the grade. Very simple example. So it is like this. There are three students, and test marks are there. The projects, homework, quizzes marks are there. I want to get the what is that their grade, and their tests weightage, projects weightage, homework weightage, quizzes weightage are given. What is simply done? Try to put it as a matrix. These test, project, homework marks, they are put it as a matrix, as a what is that, 3 cross 4 matrix, and the weights are given as a column matrix. When you multiply these two, it results in 90, 77, 87, which gives me the grades of the student. So a simple problem tells how matrix can help to formulate a very simple problem. Okay, well, let it be there. There is a software for students to use WinMat. A very free software is there which can use to study the various small properties of matrices. Just to next, see, there are mathematical modeling is a ocean. It's a ocean, and it's developing day by day. And the people are trying to see which. So earlier it was like this: pure max guys were there. Okay, so they will study algebra, real analysis, function analysis, and all that graph theory in pure mathematical perspective. There will be theorems and all that. Everything is there. Slowly, when earlier this applied mathematics would mean only statics and mechanics, okay, that people used to recognize them as applied mathematics. Now what happens, this mathematics have come in one terms with the real life problem, and many concepts are being developed to solve the real life problems. Okay? Many are there, I am touching one by one. Okay, I am this idea to create curiosity. One more kind of modeling is graph theory modeling. Graph theory is a tool with what's that points and dots and lines. Dot lines joining dots. You can see several examples over there. This is essentially same drawing, different drawings of same graph, Peterson graph. Different drawings are there. This is how the graph theory started to having to cross the bridge of Königsberg with crossing one bridge only once. Such problem was there. It was solved by converting it into a matrix. Then the postman problem is there. A postman is supposed to visit a tree only once, so that he visits all streets. That is converted into a mathematics problem, graph theory problem. Then similarly, the sweeper problem is there. The sweeping machine has to visit each street, whether it is possible. That is converted into a graph problem. You will see the problem as well as the conversion into graphs. Okay. Now I will show two typical examples of graph theory. One is this Sudoku game. It is solved using graph coloring. See, it is something is called a concept called coloring is there. Yeah, it's a concept is any map can be colored with four colors. That is, if you have India map, I want to color the state so that the adjacent states have different colors. How many minimum colors do I need? It says I need four colors. So I can use it for solving this game. I have given just a highlight. Okay, use every cell represent a vertex and the edge joining two vertices if they are on the same row on the same block, and this can be solved. And this is seen in the book Graph Coloring, and its real-time applications and overview. Okay, I would like to you to get into that. Okay? So my idea is not to elaborate into graph modeling. One more I will tell, the problem of timetable that we come across often in educational institutions during exams and all that. We get into the problem of timetabling without clashes. Those who are, I have been the controller of examination for a university, wherein there will be dozens of examinations happening on the same day. For a semester, 1,000 question papers might come in, and I must frame a timetable which without clashes. Okay, a student may be having so many exams to happen along with regular and arrear subjects, and how to frame a timetable, academic timetable or exam timetable or any other timetable without clashes. For this concept, graph coloring can be a model is given over there. A timetable problem is given on the left, and a mathematical modeling is given on the right graph. And if you, after framing it as a graph, get into coloring, method of coloring, and what do you do? Solve the coloring problem, get the minimum number of colors. Then each different color will give you different slots in the exam scheduling. So graph theory is a powerful tool. In fact, I have seen researchers with connecting this graph theory and protein structures in what is that? In studying the digital forms of the molecules and how the drug interactions may happen in a molecule, that is studied along just like a graph, not in a real situation, real lab. So one can study it using graphs. Well, there is a software for this graph theory also that is free. I love this software. I am just presenting it there. It can do various things like it can compute the metrics, it can do the coloring, automorphism, shortest path distance, maximum capacity bus, and all that is a free software available on the web that can be used. So what you do, take a model, convert into a take a real life problem. If it is convertible into a maybe shortest path problem, many such are there which are convertible into a that can be perceived as a graph theory problem. Come into a graph theory problem, plot it on a software, solve it, and get back to the original problem to interpret the answers. Well, now I get into my favorite topic for the maybe for the next 1 hour. I want to concentrate on, I mean, at least I must tell in detail about at least one aspect of mathematical modeling. So I told you many mathematical models are there, and each one will suit a typical real life situation. Okay, and differential equations won't suit every possible real life problem. Differential equations are mostly suitable for engineering models. For engineering models like this pendulum problem and the spring problem and the electric circuit problem and all that. Differential equations are suitable for that. And when the data is arranged in terms of rows and columns, if you succeed doing it, and if the problem involves the what is this interaction between these rows and column, then matrix is a best model. Matrix is a best model. Same problem can be modeled in different. For example, the shortest path problem is there. That is the shortest path from one end to another end. Various options will be there. Maybe if a fire engine has to go from one end to another end, various streets, a lot of streets will be there. Where do you get the shortest possible route from one end to another end? This can be solved as an operation such problem. It can be modeled as a graph theory problem also. So there can be one or more models representing a situation, and the correct modeling can be learned only through experience. Can be learned only through experience. Then what did I say? There are few models I didn't touch. In computer science, you have the concept of compilers. If I have time, I will show it to you. You have the concept of compilers. A compiler design paper is there. To understand this compiler design paper, no question of the applicability. It is there living in the heart of all programming. Okay. To understand this compiler design in a better way, you will have to learn a mathematical concept called automata. Automata. Okay. If I have time, I will get into that. Okay. You have a concept called automaton, maybe the finite state automaton. Finite state automaton. If it is studied neatly, a computer can be designed as a finite state automaton. For example, finite state automaton examples are your any weighing machine, the platform ticket vending machine, the soft drink vending machine. It will vend you coffee, tea, whatever you like. Such machines are finite state machines. They move only between finitely many states. They will sit. They will be sitting idle. If you insert a coin, it will start working. If you don't insert a coin, it will say something. Maybe the ATM machines. Okay, it depends on they work on finitely many inputs and they have only finitely many states. Okay, so such a concept is called automaton theory. If you model computer with an automaton, okay, then you understand it better. The how the computer is supposed to work, how certain programs may work. It will help in designing the compiler. So that is one. So we will not get into that. So let me get into this concept of optimization, optimization problems. The world, there are many optimization problems. We want to optimize many things. For example, I will have a very simple optimization problem. I am asked to go to the market. Okay. Maybe my Garwali asked me to go to the market, get some vegetables. Okay. Get some vegetables. I obviously have constraints. The first constraint is the money I have in my pocket. Maybe I have 500 rupees. Should be enough to get vegetables these days, right? So the money is a limitation in my pocket. Another limitation, I have a what is that shopper in my hand. It may hold some 3 to 4 kgs only. That has got limitations. Then the availability of the vegetables is another limitation. If I may be expecting to get chow chow over there, it might not be there. Okay. And I might want only 2 kg, there may be only half a kg. There will be many things, constraints are there. So there will be constraints. There will be constraints in an optimization problem. How do I optimize? What is the question of optimization here? See, my objective is to get as much vegetables as possible with least cost. So I want more vegetables. What do we generally do? If some vegetable is costly, we will skip that and go for a cheaper vegetable more. Okay? If onion is costly, we will minimize onion and go for more tomatoes. Okay? This is the variability of solutions. And the objective is to get minimize the cost. So minimize the cost and get the vegetables I need. And the constraints will be there. Many constraints will be there. One of the constraints is my money. Other constraint is my capacity. Other constraints, managerial inputs for a real life problem may come then and there. For example, Garwali may just call over phone and tell me, don't forget to get at least 1 kg onion. That's a constraint now. Okay, your bag can hold only 4 kg, and already 1 kg of onion is put on reserve. So onion must be purchased irrespective of the cost. Okay. So in an objective, in modeling a optimization problem, it will be something like minimization of x, fxy, with g of xy equal to 0, h of xy greater than or equal to 0, something like this. And I will have variables over there, variables, solutions. Okay, I need to know what should I solve. And the objective function will be there. Okay, and I need to get compromise between the money I have, the rate of the market, and the vegetables I need, okay, and the capacity and the requirement of minimum number of minimum requirement of vegetables, all that is there. Such optimization problems mathematically, I call them linear programming problems or non-linear programming problems or goal problems or simulation problems or queuing problems or game theory problems, replacement problems. Many such optimization problems are there. Okay, I will try to elaborate at least one or two. So this is my broad topic that I am going to get into: modeling and solving optimization problems in operation research through Excel and Solver. I depend on Excel and Solver because they are freely available. There are other softwares are there to solve optimization problems. MATLAB is there, and many paid software versions are there. Smaller softwares are there, but I prefer this Excel for college students and teachers because it will help them to visualize the things in a better way. You need not get into the cumbersome thing of framing them as equations. I will show them. Okay? And you need not write x1, x2 in Excel. You can use those functions available in Excel to do the calculations for you. And there is a concept called solver in the what is this Excel, and the open solver is freely available, which can solve optimization problems of thousands of variables. Let me tell you, thousands of variables. And yet to find a real life problem with thousands of variables. Maybe in Olympics you have thousands of players participating in thousands of games. To schedule them, you may schedule them at the minimum possible time. You may need something. Right? So this generally it is called operation research, and the schematic, the representation is given in this slide. Just have a look at it. Yeah. I derived this concept from essentially from two books: Introduction to Management Science by Hillier and Hillier, and a book by Anderson. This concept is called management science. It involves after real life optimization problems, not this engineering optimization, which are usually solved by differential equation modeling. This concept OR is described in this slide. Operation research taught to engineering students, science students, and business students. It essentially helps in decision making. It essentially helps in decision making. Let me give a list of problems which can be modeled and solved using operation research. Just a list. So I can model finance. Finance models can be attacked. Investment models can be attacked. I will share this file in case you need. Investment models can be attacked. Production models can be seen. Purchasing models can be handled. Distribution and logistics models can be handled. Scheduling models, decision making models, project scheduling, networking, these optimization problems can be handled. And elementarily, transportation, assignment problems, inventory, queuing models can be handled. Right. Just waiting for the slide to come. Yes. Yes. What are the phases in this kind of optimization modeling? Identification of the problem. First thing, see there, the first one we saw the length of the length and the breadth together is some number, and the difference of the length and breadth is some number. What is the length and what's the breadth, what's the area? So this is a problem. You identify it to be a geometric problem. You draw the rectangle, okay? Then construct the model. Then the method to solve them is the solving equations. Derive the solution. You test the model. and after establishing controls, you implement the model. There are various processes in operation research: allocation process, inventory process, waiting line queuing process, and replacement models. Replacement models are like this. Suppose I have a very big building, maybe a 14-story building, and I have a lot of lights and lights hanging over there. LED bulbs are there, and there can be, see, when as and when a bulb fails, I can replace it, or I can replace them as a whole. So replacement problems can be optimization problems. Queuing problems are everywhere. Queuing problems, maybe in banking or this and that. How will they help to optimize? See, suppose there's a lot of queue in the banker with the banker. Okay, then I may be interested to know whether it is required to have one more teller or not. How will I justify it? I will simulate and calculate the waiting time in the system, waiting time in the queue, and all that. And in some cases, we may have to look into the inventory also. Okay? And the allocation process, I will show you. Now I will show you a list of optimization problems. Just as you see these snacks there, you should induce curiosity in you. Trying to solve any real life problem is mostly optimization. Without optimization, you won't have a problem on hand. If everything is, I have a lot of money, I have a lot of space, there is no optimization. I keep on accumulating anything. Okay? So optimization gets in when you are really serious about real life problems. Just have a look at these such problems. I am starting with a very elementary, simple problem, simple word problem. It's a cabinet maker problem. Okay? So elementary problem only. This cabinet maker has 12 units of woods and 36 hours of labor, and intends to build two different kinds of bookcases, model 1 and model 2. And there are requirements. Model 1 requires 3 units of wood and 9 units of labor. Model 2 requires 2 units of wood and 8 hours of labor. And I have the selling prices of $150 and $90. How many models should I prepare so that my revenue is maximized? See, the first thing that a max guy does is to model this as like this. The typical mathematical model. Just have a look at it. Have a look at the problem. The maximization depends on 150 and 90. That is put as the total revenue is put as Z. And one constraint, the total wood requirement is put as one constraint. And the total labor requirement is put as another constraint. And the non-negativity constraints are there. But the Max fellows are comfortable with this kind of modeling, and we solve it with a concept called the simplex method, two-phase method, Wiggum method. Many such things are there, algorithms are there. Commonly simplex method, we use it, solve it, and get into the solution. Okay, but alternatively, for the benefit of those who are scared of writing this equation, I will hide them in spreadsheets. Okay, I will show how that model is there. This is how it is modeled on a spreadsheet. I will tell you one example at least I will illustrate. Okay? Just have a look at it. You are arranging it as a form of a matrix. Okay? You see the colored ones. I will tell you how to model this and solve it. I will start with a simple example. So before getting into that, let me expand the problem. Okay. Now earlier there were two models and only one wood and one labor. Now I have five models, and I have plywood, rosewood, redwood, three kinds of woods. Okay, and I want 5 different bookcases to be designed, and each model requires plywood, rosewood, and redwood as applicable, and the selling prices of these models are there. Then how many of each model should I prepare so as to maximize my revenue. I'm expanding the problem. Okay? And you see that the model here can be very simply expanded like this in a spreadsheet model. I'll tell you how to do that. At least one I will illustrate. So this is how you are expanding. So this is one model. Then I can go for modifications of this model, expanding. So one is very simply how many models should I produce? How much number of model, one model, two model, three model, four model? That is a simple question. Then in optimization problems, I can get further inputs. One is there is a survey and the maker feels that he cannot sell more than 50 numbers of model. Suddenly a constraint is coming in. I cannot produce more than 15 numbers of model 5. In this situation, what do I do? Right, that is one. Okay. So that is solved here. Hmm? Okay. Then one more. I want to a regular customer. See, you may choose to, its solution suggests that you produce only model 5. You can see the solution here in the yellow ones. It says model 1, model 2, model 3, model 4 are not at all profitable. Don't produce anything. Produce only model 20. This is okay. But a regular customer is sitting there. He wants one bookcase of model 1. You cannot ignore him. You will have to produce at least one bookcase of model 1. Can the maker entertain the order? If I entertain the order, what is the impact on the revenue? That is another question. Okay, that is put here. It says, yeah, you see that when everything is produced, the revenue is $1,400, and if I introduce one constraint, then it goes down to $1,250. And if I produce one model one compulsorily for the regular customer, then my revenue comes down to $1,200. And the third one is one more. The maker feels, see, models are there, but unless you make one each in each model and put it on the showroom, people may not purchase. So I want to put keep one model in. If I do that, then what happens? The revenue further goes down to $900. So this will throw me light on. See, mathematicians cannot be blindly doing something. So you gave some statistics. I have done the model under this is solution. Keep it and go away. You cannot say. And there will be a live problem will have various inputs. It is dynamic. Live problem is always dynamic. You will continue to get inputs, and you should change your model accordingly so that the optimization problem gives the best to the customer. Right. Now, let me explain this. Shall I get in show one more model? I will show one more model. Yeah, the different kinds of models, different kinds of problems that can be brought under the optimization category. A florist company problem. See, a florist is there, and he is producing a different kinds of bouquet. 4 different kinds of bouquet are there, and he wants to know how much to produce of each bouquet. And there are various varieties. Each bouquet uses 5 kinds of flowers, and Japanese rose, gilliflower, and all that. The availability of those roses, those small flowers are given, and the cost of each flower is given. And 4 varieties of bouquets are there, posy, rosy, and all that. And each bouquet will have different combination of flowers and different selling prices. Okay. Now have a look at this. Under this situation, how many bouquet? These are called allocation problems. I mean, optimization problem. How much bouquet I must produce in each category so as to maximize my selling price. So you see that this kind of thing has more variables now. It has got 4 variables, and the modeling is getting bigger. Okay. Then one more combination, a mixer problem. A eat mix mixer company is there. See, whenever you go to this sweet shops, what you generally ask, you may ask for a general purpose, for gift purposes, you may ask, give me assorted sweets. So it is up to the seller to give you 1 kg assorted sweets so as to suit your pocket, so as to suit his strategy also. If you see at that assorted, you will see certain sweets will be more in number, certain sweets will be less in number. How does he decide which is sweets to be more, which is sweets to be less? So it is like this problem, and I have three types of flakes. I have in every mixture you have got flakes. Okay, groundnuts will be there. The poha can be there like that. They are called flakes. And I have four types of mixtures: A, B, C, D. Madras mixture, Goa mixture, Bombay mixture, like that. And there are now it becomes difficult. Constraints become difficult. It says for a mixture A, flake 1 not less than 20%, flake 2 not less than 50%, flake 3 not more than 25%. So with this combination, this mixture A has to be produced. Selling price is 10. And similarly, B, C, D have different combinations of the flakes. For example, in D, F1 is not less than 50%. In A, F1 is not less than 20%. It varies. So the tastes of the mixtures also vary. Hmm? And the constraints are there. Plant capacity is there. How much flakes to be produced per day, and the manufacturing cost per kg, everything is there. You cannot say, see, I am this flake D is selling price is $25. Produce all flake D only. People may not purchase, and I may not be able to produce all that. Okay? I have to cater to needs of all, and at the same time taking care of my profit prospects also. Right. Such a model is given here. This has got more variables now. This has got 12 variables now. Hmm. Now, uh, to interest this engineering people, I will get into uh, energy sourcing problem. Hmm. See, uh, a company is there, energetic company, needs to make plans for the energy systems for a new building. Okay. For a new building, I need to plan the electricity sources. Where from do I get electricity? Electricity, I need 20 units. Heating water means I need 10 units. For heating space in the building, maybe in the colder regions, I need 30 units. Right. From three possible sources of energy, I can get directly from electricity. If there is a possibility of natural gas, I can make use of natural gas, and solar heating facilities can be used. Okay. Solar heating facilities are cheaper, but installation cost is more. Running cost may be cheaper. So in these cases, what do I do? I put the problem. So this is a real life problem on how to design a new building, how to decide the proportions of the sources of current. Okay, and you cannot put everything solar. That solar panel is limited by whatever I have on the rooftop. The space on the rooftop limits the you cannot have everything as solar. So how much I can get it from natural gas, how much I'm getting from solar heater, how much from direct electricity, this can be modeled like this. Okay. Then right, this product mix problem. I am showing a variety of problems which you can think of modeling as an optimization problem. See, when you have products, they may have to be produced in a particular ratio. For example, if you produce one car, four tires have to be produced. For each car, four tires. So 1:4 has to be there, right? So like that, for some, the company produces five products, they have to be produced in a particular ratio, 1:3 is to 4 is to 2, 1:3 is to 3 is to 4 is to 2. And these products use three materials, 1, 2, 3. And each product will require various capacities of the units 1, 2, 3. Okay. The what is that? The materials 1, 2, 3, and the available units of material 1, 2, 3 are there. They are given. You can see them, and the selling prices are there. Find the optimal production of the products A, B, C, D, E, which will maximize the revenue. This called a product mix problem. Product mix problem, right? For example, if you produce a nutrition mix, it must have certain percentage of rice, certain percentage of wheat, certain percentage of millet, certain percentage of sugar and all that. So how much should I produce so that I maximize my profit? So this is called the product mix problem, which can be modeled like this. I will tell about one or two models when I, in the last half an hour, I will try to impress upon you how it can be solved. Another model that comes often in this optimization problem is quality checking. In any engineering discipline, any factory, you come into this quality checking problem. That means there are various varieties of quality checkers. Just have a look at the problem. Just have a look at the problem. It's like various quality checkers are there, and each quality checker can do it with certain accuracy and certain charges and certain lapses are there. For example, quality checker 1 can check it with 98% accuracy. He will charge us $20 per hour, can check 50 pieces per hour and like that. And to drastically going down, the level 5 fellow will, excuse me, yes, 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 Poliye. I'm in a webinar. Can I talk to you a bit later? Okay. Venugopal, I'm on a webinar. I'll talk to you a bit later. Yeah, excuse me. So there are five, I told you quality checkers. You cannot say one quality checker does it with 98% accuracy. The lack of accuracy will result in cost for the seller because if 2% deficiency is there and 2% unchecked, I mean, not quality products go out, they will be returning. They will be returning to the seller and the seller will incur loss. Okay, but I cannot have all quality one level one quality checkers. May not be possible. They may not be available, and it will give me make me more cost. So I have to compromise. I have to compromise between. I have to compromise between what is that the quality and the cost of faulty checking and all that. So how do I get to the how do I minimize the cost to attain the best possible quality? Okay? And you will come across this in various this kind of assignment problem. This will come up. This will come up in various very simple application in your institution. It can happen. See, our institution has what is that? Maybe arranging a function, maybe a webinar, maybe a convocation, maybe some conference, something like that. There will be various tasks associated with it. Right from climbing a pole to putting rangoli and arranging food things. Many things can be there. Okay? And the performance level will vary from person to person. The person who can climb a pole may not be able to put rangoli as effective as the that person. One person can drive a car and the other can drive it with more perfection, faster. Okay. So what job to be assigned to which person? Such kind of assignment problem to maximize efficiency can also be attacked. It is also called the optimization problem. The trick is in some of my PhD students have done in optimization problems only for real life problems. For real life problems, one has even done it on what is that wholesale vegetable market. One did it on network of temples. Okay, so one did it on queuing, visiting the network of tourist places. The eyes, if you keep your eyes open, a problem can easily be converted into a mathematical model. So this is how it is modeled here. I will explain this. Then scheduling problems can be attacked. Scheduling problems. What are they? See, this comes in maybe in supermarkets, maybe in bigger concerns where you have where which work in shifts, which work in shifts. Maybe there are many shifts. from 8-hour shift, 6 to 2, 10 to 6, 2 to 10, 6 to 2, 10 to 6, and 24-hour cycle is there, 8-hour cycle is there. And I need to appoint doctors there for the shifts. And for each shift, the charges of the doctor will differ. Okay, the late night charges will be more like that. And my experience says I always depend on data. My experience says for every 4 hour, the big hospital, how many doctors I need. That's a calculation that is given here. Although the shift is for 8 hours, the slots are for 4 hours, and every slot I have some observation. From 6 a.m. to 10 a.m. I need 50. From 10 a.m. to 2 p.m. I need 75. From 2 a.m. to 6 a.m. I need 25, and etc. 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 is there. Now, how to see? You see the problem of optimization. The shifts overlap. First shift is from 6 to 2. Second shift is from 10 to 6. 10 to 6. That means a 4 hours overlap is there. So the fellows who come for the first shift and fellows who are coming for the second shift will will have a overlap during 10 to 2. So during this overlapping period, how do I minimize? That is the main optimization problem. How do I minimize the number during this overlapping period so as to achieve the minimum requirement of doctors, so as to minimize the cost of recruitment of doctors? So this is put as a bigger problem. Have a look at it. But each one is modeled differently. That's what I want you to see. Usually, I do these things as in a workshop so that I make these participants work on this, understand this problem. Here, I'm not doing it. I'm only demonstrating. Each model will different. See, the model of this looks different, and the model of the scheduling problem looks different. Okay. Then a media advertising problem can be there, can be an optimization problem. Media advertisement problem can be an optimization. Like, see, when I want to advertise, when I want to advertise hmm, to various channels, maybe dozens of newspapers, dozens of television, dozens of radios, and where to advertise, which time to advertise, so as to maximize the reach and to minimize the cost. Such problems are always there. They are called advertising problems. Okay, and this problem can be a bigger problem that can happen everywhere. Maybe our administration may want us to advertise in various medias so as to minimize the cost. The students can take it as a small project and do it for them. Okay? And the cost will differ for days. For weekdays, different costs will be there, and during different time slots, costs will differ, exposures will differ, and how to do this. This is one. And hmm, yes, now it's time to illustrate the at least one. I will start with the minimum one. I will illustrate at least one. Okay, this one I will illustrate the shortest, smallest problem. See, how do I do it? How do I design it and solve it? First, what you do, you put them, you forget these colors. Okay? Don't frame, you need not frame it as a mathematical model also. Just put them as this, let me make it bigger. Okay. Just put them in matrices. You have a look at the problem. Have a look at the problem. It's like two models are there, model 1 and model 2, and the wood requirement is there, labor requirement is there. Okay. Arrange them as a matrix first, trying to juxtapose the model 1 details in column and the wood labor details in row so as to bring them together. Okay. Now what do I do? These blue ones are my data, okay, obtained from the problem, and here blue ones are the data. The first thing I do is to find out the, what is that, variables. How many variables? Two variables are there, model 1 and model 2. how much use in model 2, the Excel has given me the answer. I will erase that. I will erase that. So these two blank cells will get the solutions through Excel. That is right. Next, what do I do? Let me compute the revenue. I will compute the revenue and put it on place. How do I do that? What's the revenue? The revenue is if the number of bookcases, if I do here is X1 and X2, just for the sake of clarity, I am putting those numbers there. Hmm. So this 150x1 plus 190x2 will give me the revenue. How do I do it? How do I do it? I use a function called sum product. Sum product is the sum of products. What two products are there? 150 into x1 is a product, 90 into x2 is a product, and I am summing them up. And I am summing them up. It is a very simple tool. You put equal to there, start with some product, open the bracket, and mark the row which you need to multiply, and mark the other row which you need to multiply with the first row term by term, close the bracket and put the enter. That is the sum product function. Then you need to compute the constraints. What are the constraints? 3 units of wood or needle for model 1, 2 units of wood or needle for model 2. But how many total woods I need? 3x1 plus 2x2. I need 3 into x1 plus 2 into x2. How do I achieve it? How do I achieve it? I come here, again put to some product equal to some product. I am illustrating only one so that you share this Excel sheet so that you can try. I will shade this wood, what is this wood needs, and I will shade this x1, x2. Okay, then you can see in the formula some product of the two rows come up over there. So you should first put the objective function using a sum product function, and accommodate the constraints, and put the variables in blank cells. Put the variables in blank cells. Nothing should be there. Okay. And then a concept called solver is in the data tab in any version of Excel. I am using 2007 version, but still a newer version also have this somewhere in the data tab, or you can make use of open solver, a freeware available on the web. Let me go to this. In the data tab, you will see the solver add-in. Go to that solver add-in. In that solver add-in, point out to the target cell. Point out to the target cell, which is the objective function cell. Then mark the variable cells, changing cells. They are the variable cells, the two blank cells. Then you mark the constraints. Constraints can be added with the add button. Go to the add button, enter the left side here, enter the right side here, and click OK. The constraints are put over there. Constraints are put over there. Then you can go to the solve button. You can go to the options and say whatever you need there. Assume linear model, assume non-negative. And if the model is really bigger, you can set the number of iterations, precision tolerance, and all that. Okay. Then just click solve. You see the blank. What is that? Cells are there. Their answers will come. I'm solving it. So it is telling me 4 and 0. That means to produce 4 of model 1, 0 of model 2. And you can see here, I can get the sensitivity report also. What is a sensitivity report? Sensitivity report is not available for this. Sensitivity report is one. See, I am given some data. With what sensitivity I can change the data. So I say 12 units of wood are available. Can I make it 10 or can I make it 14? How far I can go so as not to affect the revenue that is calculated. Revenue that is calculated. This is one. Okay. Now let me tell you how to expand this problem. How I am expanding this? I told you I can expand it to further model. So this is how it is expanded. You can just insert columns. You can insert columns and come into this. This is please keep in mind this is a demonstration. I am not able to work it out fully make you work on it. But have a look at it. You should induce curiosity in you whether such different models I will show, further models I will show, so that one of the real life problems can be brought into one of these optimization models and solved using one of the techniques of operation research, so that real life problems can be solved mathematically. Hmm. Have a look at it. See, earlier there were two constraints. Now there are four constraints. Models are there. Same kind of thing is modeled here. Now, same thing. If I go to solver and ask him to solve, so it will give me the answers. Right now, let me go to further models. So this is how you what you do. Very simple. You need not scare yourself with the equations. Like I told you, this is a problem. If you write it mathematically, you will have to write it as an equation here. Don't be scared. You can just plot it in the Excel sheet and solve it with Excel solver with very little Excel skills that you know. That only few functions will be used for, such as the sum product function is used. Okay? So you need not frame this as a mathematical model for a bigger problem, but mathematics is hidden there and you can solve it using Excel. Right. Let me go to further model. These are linear model. Let me go for ah, maximal flow problem can be attacked. Maximal flow problem is a real life problem. What is this? For example, um, these days, a certain area, a certain city needs lot of ventilators suddenly. They need 100 ventilators to be rushed from any part of this country to that city. They need 100 ventilators there. Hmm? How do I do? I am least bothered about the cost. I can make use of the flight. I can make use of helicopter. I can make use of train, bus, car, whatever it is. Okay. I want to flow the rush the number of ventilators to the particular place urgently. Okay. And maybe medicines. Hmm. A certain malaria medicine I may need at a particular place in large numbers. There might be an outbreak. Then I will have to flow the medicine from various sources, various paths, various resources to that place. So this is called a maximal flow problem. The flow should be maximum. Okay. Now this a small model I have taken from the book I cited. This is a from a particular place, Stuttgart to Los Angeles. I have to flow through various means. So I may have to send the materials through train, through bullock carts, through boats, and there will be restriction in each of them. A boat can hold only few items. A flight can hold more. A ship can hold more. But ship will shift to very slowly. Ship cannot go fast. Flight can go fast. And all those constraints you must result in maximal flow at only one particular place. You might have experienced it in many. See, money flow can be imagined. Okay, money should flow to me. I need 1 crore immediately. Hmm? I will ask whoever available. I will ask. Somebody will send through NEFT. Somebody will send through DD. Somebody will send through somebody also. But I need maximal flow of money. Hmm? It should come to me in whatever source I want. So when I need money, I will view it as a maximal flow model, and the maximal flow model can be attacked as a what is this optimization problem? It's called a maximal flow problem. Maximal flow problem. Okay, here I don't optimize anything actually. I am concerned only on the flow. I don't bother about the cost. But the flow is important here. So this can be modeled. This can be modeled. I will show it to you on the Excel sheet. I prefer Excel for teaching. Although people may say other models, other softwares are there, but Excel is very easy to teach, learn at college, university level, and even for solving real life problems at research level, I have used this. See, here the only function that I use is what is this? Ah, yeah, the function I use is sum if to calculate the net flow, you can see there I am using the sum if function available there. So with just using the sum if function without bothering to model it actually as a mathematical problem with the equations variables, you can just put it on the throw it on the Excel sheet. Any maximal flow problem that I say, okay, maximal flow problems can take different outputs, can come from various sources. You can think of it something. Maybe if you are doing a rangoli, I will need a lot of colors to flow to me immediately. Whoever has it in whatever home, they must bring all colors to me. That is a simple illustration of a maximal flow problem. This can be attacked, right? Then what else? Yeah, the shortest path problem. Shortest path problem comes to us in various ways. Okay, I will have to travel from one place to another place in the shortest possible route. Shortest possible route, especially for a fire machine, fire engine. It needs to travel through the shortest path immediately to that place. This problem can be attacked. Just to see the model, it is different from the optimization model. Okay, the resource allocation model, the whatever model we saw, their advertisement model, this is a different model. See, each model will need a different method of attacking the problem. Hmm. Let me show the model to you on Excel sheet. If you need, I can share these Excel sheets to you. They are open. See, here the function I use is again sum if function. For network problems, this is a network problem. A sum if function can be used. Hmm. I'm afraid I cannot illustrate this now. It takes time for me, but just have a look at it. It tells me the total distance, and if 1 is there, that path is on the route. If 0 is there, the path is not on the route. It won't draw you diagram, but once I feed it over there, I can very quickly decide the path. Wherever 1 occurs, those paths I will see, and I will see minimize the total distance that is covered. So shortest path problems can be attacked. What's more, very simple transportation problems can be seen. Transportation problems. Transportation problems come when you have to transport goods from various locations to various other locations, right? It may be like cycle production. Cycles can be produced in various factories and it will be sent to various shops. Okay? So this is a transportation problem from which location to which dealer so as to minimize the cost. Suppose you want something in Patorda, you will try to get it from Goa rather than from the southern end of India. Okay, that is farther away. Maybe from Kanyakumari, you might not wish to get something, but you can try to minimize whatever you get from Kanyakumari. Okay, but you can maximize whatever you get from Goa. But from Goa, you may not get as many cycles as you need. So you may have to get it from Chennai also. You may have to get it from Chennai also. So it is not always easy. And one of my students did the transportation problem for of transporting over 100 vegetables and fruits from various parts of India to a particular part near Chennai. So that was a real life transportation problem that we attacked. Okay. So these transportation problems can be very easily attacked as matrices. Just have a look at it. It is done like this. It's very easy. Again, only a sum product function is used here. Very simple. You arrange the data as matrices and you put it as another matrix wherein I would like to have the answers. I can erase it now. Okay. Then at one stroke, you can check it to be a balanced problem or unbalanced. What's a balanced problem? The supply equals demand is one issue. Supply greater than demand is another issue. Supply less than demand is another issue. All can be very easily attacked in these models. Another advantage of these models, both academically, you can give as many optimization problem as you want to your students. If there are 100 students in a class, you can give 100 questions, right? That is one. Second, Teachers can develop a lot of question banks on this. Using these techniques, students can try solving the problem given the textbooks with these models. Right. Next, to develop question bank, I told you. Next, to do research. When you get into solving maybe a MSc project or a MPhil project or a PhD project, when you want to see a problem, PhD problems are plenty. See, I have guided over 10 PhD students, and I was the director of research in my previous with a previous employer. I was the director of research. People would usually ask me where to go for problems. Please give me a problem. The problems are plenty in this world. Take any real life problem. If you model it mathematically, then you can solve it in a mathematical system or using a software. And then you can help solving the real world problem. That will become a very good thesis. That will become useful to society also. So what do we do to recognize the mathematics in those problems? Mathematics in that real life problem. Real life problem will be presented in words only. But whether you convert it into a simultaneous equation, whether you convert it into matrix, whether you convert it into graph theory, or convert into a operation such model, or convert into a automata model, it all depends. How do you perceive it? If you understand the model, you understand the problem in better way, you can easily model it mathematically, so that mathematics can help you in solving, validating, authenticating that particular model. Okay. So this is how I do. Here simply I can solution is got in seconds. Modeling takes time. Modeling takes time. It has to be done intelligently with the all skills of Excel. So I am just getting the answer here. See, nothing to transport from 1 to A, 50 units to be transported from 2 to A, and 10 units to be transported from 3 to D. And this is the concept. Here, what more can be done in this transportation? Suppose I may not be able to transport from one location to another. That can be immediately incorporated in this model as a constraint. And I may have to certainly transport certain units from certain location to certain other dealer. Okay. And from location 2 to another location 3, road may not be all right. So from location 2, location 3, shifting is not possible. So I should block shifting there. I should block transportation there. So any constraint can be immediately incorporated in this model as a constraint, then solutions can be obtained. So real life problem will have lot of constraints propping up then and there. Then and there. A model presented to you will be different. But when you start solving the model, people will give different inputs. See, for example, students can look into solving an optimization problem for a simple bakery in their neighborhood. A baker's problem is an optimization problem. See, a baker uses certain flours, certain creams to produce what is this puff, cake, donuts, and all that. Okay. How much donut he must produce, how much cake he must produce. What does he do? He does it with experience. He does it simply with experience. He doesn't have a mathematical validation of that model. Okay. So you can simply get into the bakery and ask how many resources you have, boss. What is the money you have on hand? What is that you must produce? What is the demand for the donut? What's the demand for cake? What's the demand of puff? What's the demand of this? That you can ask. Make everything. Make it as an optimization model or simulate it. Simulation is possible through mathematical modeling. Simulation can be done. I will show it to you. You can simulate and make it as a successful optimization problem for college level projects. Hmm? You must have seen lot of mushrooming. What is this agents who say we do projects for engineering students, we do projects for science? Why, sir? The projects are available in your neighborhood. Go to any neighborhood. Okay. For example, very simple problem. You may have to computer lab is there. You have to put two shoe racks over there. How much pigeonhole should be there in the shoe rack? That can be a simple mathematical model, simulation model. Somebody can simulate and tell you how many parking slots must be there, how many seats must be put in the reservation counter, how many chairs must be put outside the principal's room, whether 4 chair or 5 chair, which is optimal. You cannot put 20 chairs there. How many visitors are expected per day? That can be a very small project. Projects are plenty. That's what I want to say. Real life problems are plenty. Okay. Then this one is transportation problem. Another is assignment problem. What's an assignment problem? Right from allocating papers to teachers, it is an assignment problem. See, which teacher will give the best when allotted to which paper? That can be a very simple study in college. That is a assignment problem. Another, the routing problem. See, for example, if you see here, there are four companies and they are bidding for four routes, school bus routes. To which company I should give the offer so that I minimize the cost of running the four bus routes. This is a very simple problem. This optimization problem can be designed as a assignment problem, right? Then variety of decision problems can be attacked. I know I am fast, but I will be happy if the viewers get an idea how the optimization problems can be modeled mathematically. Various optimization problems, I touched upon various now. I will touch upon few more. Decision problems can also be attacked. What are these decision problems? Maybe in the era of vaccines, a local doctor may have to store various vaccines. One for smallpox, one for corona, one for this, one for that. Okay, child's vaccines are there. How much vaccine should he keep daily? How much vaccine should he order? Okay, that is a decision problem. And for even for a college, how much chalk piece I must order? That can be a very simple decision problem. Okay, what do you do? What do you do? You usually the what we do, we usually keep on purchasing. We keep on having inventory, and sometimes we will end up having more chalk pieces in the storeroom. Sometimes we may purchase more, and they may be wasted. Okay, why don't you attack it as an optimization problem? The requirements of the college, requirements of the university, requirements of the company, inventory requirements can simply be attacked as an inventory problem. Okay. Now this problem, let me just have a look at it. The company has three face washes: oil face wash, dry face wash, silky face wash. And this is how people receive it. Okay, can turn out to be a good product, can out to be a moderate product, can turn out to be a poor product based on certain probabilities. How do you get the probabilities? You get these probabilities through experience only. See, you can make the list of those data, and over years, if you do that, you can simply go for Monte Carlo simulation that can be done on Excel. You can go for Monte Carlo simulation, simulate it, and get the probability also. Okay. Now, so with this, it can be put as a tree. It may be a wonder for you to know that Excel can draw trees. I will just show it to you. There's an add-in which draws decision trees on Excel. I will show it to you. It is a Excel called decision tree add-in. Is available freely. If you install it, you can see here I have drawn decision tree. Decision tree can be drawn on Excel, and the solution can very easily be obtained. Okay. So the one more bigger automation is a smooth car form decision problem. Like a car wala is there. How much car he must keep ready? 5 cars or 10 cars or 20 cars? Okay, if you go to a taxi wala, he may always send you a taxi, but he may not keep as many taxis as he needs. He may have only 5 or 10 or 20. And how to decide the number of cars he must keep there? So you see that not only cars, everywhere in our life we will come across such problems. How much to keep, how much food dal to purchase, how much grocery to purchase for the college canteen. That's a decision problem. Okay. Hmm? How much grocery to purchase? Why don't you randomly purchase and waste it? Why don't you do that? It can simply be taken up by a problem by the student. The mess problem, canteen problem can simply be an optimization problem for a worthy project, right? Okay, such problems can be attacked. I'll show it to you. How do you do that? It is done as a tree problem. You see that again I am able to draw a tree there. This is drawn with the decision tree add-in. Okay, right. Now let me conclude with the simulation problems. See, simulation is a computer simulation is one you might see on screen. 3D simulations will be there. The students now in the era of pandemic, students, engineering students do practicals on simulated platforms. That is different. What I'm going to say is how do you simulate real life problems? How do you simulate it based on data? Right. Have a look at this problem. A tourist car operator finds that during the past few months, the car's usage has varied so much. The cost of maintaining the car has varied considerably. He has observed it for 200 days. The demand for the car, he observed it for 200. That's the data. Okay. Now simulate it for one more year. I observed it for 200 days, maybe 50 days, maybe 20 days. If you want more result, more good result, you must observe it for more days. I want to simulate it permanently. What do? I will get the frequency like this. This is how you build the probability for a problem. You note down the number of trips from 0 to 5. What's the frequency out of 200? 16 times there were no trips. 30 times there were 5 trips like that. Then you go for simulation. I will just highlight it. I have a few more minutes to go. See, you can go for the simulation in Excel. You simply do Monte Carlo simulation here, go for probability, cumulative probability, and just make use of the random function. How do random function result in what is this events? See, for example, if I toss a coin, I can toss a coin in Excel. How do I do that? If I toss a coin, head appears, tail appears. But when I generate a random number here between 0 to 1, it can be either less than 0.5 or greater than 0.5. So I will tell Excel, if the generated random number is less than 0.5, treat it as head. If the generated random number is greater than 0.5, treat it as tail. Then tell me when I toss a coin, how much combination is coming. See, when you do this in classroom, so not an application, when you do it in the classroom, you are telling students the probability of getting a head is 1 by 2. Does it mean that if I toss the coin 2 times, one times I will get a head, one time I will get a tail? No, no, no. Then I will say, toss it a number of times, toss it 1,000 times, then you will understand that the ratio of head to tail is half. How do you toss it 1,000 times with on hand? Just to, you can do it on Excel. You can just do it on Excel like this. You see here, for the random number of trips I am allocating. For each random number of trips I am allocating, and I will just drag it for any number of times I want, and that tells me that the average number of trips is 2. I can keep on generating the random number, and based on random number I can do simulation on this. So this is one. Okay. Next, I think 5 more minutes. I will conclude with the queuing theory problem. Queuing theory problem is a real life problem that can be modeled and solved, understood, solved, and improved mathematically. See, there was a doctor in my neighborhood who asked me, see, how can my time can be utilized effectively so that I can minimize the waiting time of the patient. He has experienced a lot of displeasure from the patients. Patient spends more time in the queue and less time with the doctor. I want to spend more time with the patients. What do I do? Then you have to study the queue nature. How do they arrive? The arrival pattern, service pattern. And you can suggest after studying all this, after solving the queuing model mathematically, getting to know the average waiting time in the queue, average waiting time in the system, and all that, you can give better suggestion. Maybe, my dear doctor, you put a receptionist who may measure the BP and the temperature for the patient so that you avoid doing it in your room. And you might have seen for bigger doctors, the bigger doctor will not look into your medical record and all that. Before you get into a bigger doctor, a famous doctor, there will be small doctors who look into your what is that medical sheet. They will make notes of it. They will make a lot of inquiry to you, this and that. They will put short notes and give it to the doctor, so that the time of the doctor is precious. You spend more time with the doctor. These queuing models can be studied mathematically. For in a banking, queue can be there. Suddenly, the manager will write to the what is that the central office. Give me one more teller. Open one more cashier counter there. Queue is getting more. So the bank should study where the queue is more. Whether the queue is more only on weekdays. Suppose you have a bank counter in your college. What happens during the fees paying sessions period, the queue will be more. Otherwise, the fellow will be sitting there without job. So you cannot suggest one more counter over there. Okay? Right. This is a simple problem, a haircutter's problem, very common problem. So I am putting this, taking it from that book because it's a very common problem. The haircutter, the customers arrive randomly, and see what problems if he whether he must employ assistant or not. If he employs assistant, more salary will be shared to them, but you will get more customers. So his problem, whether to employ one more assistant or not, that can be simulated in a sheet like this. I will show it to you. See, the time of arrival, they can be simulated. The time of arrival is random. If he opens the shop at 10, no guarantee that 10 o'clock somebody will come. Somebody may come even at 11 o'clock. And it is not that they come in order. Every 20 minutes you will, no. Suddenly 10 customers will arrive. And you will be handling only 2 customers. The regular customers may wait, new customers may just slip away. So you can simulate it. You can just simulate the time of arrival, the time the service begins, service time ends, waiting time in the system, waiting in the queue, and you can calculate mathematically. See here, you can say the mean arrival, intra-arrival time is 30 minutes. So every 30 minutes, some customer comes in average. Minimum service time is 15, maximum service time is 29. The average waiting time in queue is 10 minutes. The average time in the system is waiting plus service is 30 minutes. You can arrive at those numbers and help that fellow to decide whether he can have a new assistant or not. Right. Finally, very brief note on goal programming. There are certain real life problems where you will not have only one objective. There may be multiple goals. There may be multiple goals. Maybe to minimize cost, to maximize efficiency, two goals can be there. So goal problems can be attacked using optimization modeling. Then whichever I didn't touch game theory problems. Game theory problems are very famous problem. See, anything in the life is a game. If two political parties compete in the election, it's a game, and they will use various strategies. One may go door to door, one may choose to give pamphlets to them, one may concentrate on addressing only youngsters, one may concentrate on addressing only the one sort of population, one may concentrate on certain groups of individuals, one may concentrate on individuals, I mean, intellectuals, like that. So when these various strategies oppose each other, which fellow wins? This is a very tricky problem. This game theory problem can be modeled mathematically and solved. You will come across game theory problem. See, a company is there. Uh, this company will produce various toothpaste, this, that, shaving cream, lot of things. And yeah, opponent company will also produce toothpaste, this. No? What strategies do they employ? So if this fellow uses one strategy, that fellow will use similar strategy or more strategy. If I go for advertisement, innovative advertisement, the other fellow will go for more innovative advertisement. Okay, how to use effective strategy, which strategy to be used in which probability, so that I succeed. So these problems are called game theory problems. I didn't touch it. Then the computer problems, computer programming models, that is the problem of ATM machine, the problem of finite state machines, problem of a vending machine, all this can be mathematically modeled. It's called automata theory, theory of computation, theory of computing. That concept is called automata theory modeling, and there are softwares available for this kind of thing also. So I will conclude here, hoping that I at least succeeded in showing what is this concept of mathematical modeling, where very wide variety of given wide variety of problems. I am stopping my presentation. Maybe few people are there on YouTube also. If there are questions, they can ask. Otherwise, see, I am prepared to even conduct this as workshops, as hands-on workshops to handle real-life problems, hoping that this will motivate students and professors, research scholars to take up real-life modeling, real-life problems, mathematically solve them. Thank you. Thank you so much. Thanks for the organizers. Happy to meet the staff of Don Bosco, especially Professor Kala, whom I could see after a long time. Greetings to all. Thank you. The organizers may please take over. Yes, please. Yeah, thank you.
Thank you very much, sir, for your wonderful session. It is very nice to know about lot of things about the mathematical modeling. So many things we are not aware of. So there is lot of importance of mathematical modeling nowadays. So hope all participants have enjoyed the session. Thank you very much.
Thank you.
Dear participants, now I'm lucky enough to introduce another speaker of today's webinar, Dr. Himadri Mukherjee, Department of Mathematics and Statistics, Birla Institute of Technology and Science, Pilani, Goa campus. He did his bachelor's degree from Chennai Mathematical Institute, then joined Northeastern University, Boston as a PhD student. He received his PhD in 2008. Since then, he has worked in ISI Kolkata and IISR Kolkata until joining BITS Pilani Goa campus. He has guided a student to her PhD and currently have 2 PhD students. He has a wide range of research interests from algebraic geometry to graph theory. We are very much thankful to you, sir, for joining the webinar. Thank you so much. Over to you, sir.
Who's the person?
Himadri.
Mic is off. Says mic is off. Says mic is off.
Where is the meat one? Where is the meat?
You just say. You just say.
Meat. Where is meat
You
gone?
speak. You speak.
Directly. Hello, sir. Sir, please unmute your mic. Dr. Himadri, please unmute your mic, sir.
Okay, yes. Sorry, I forgot to unmute myself. Thank you, Professor Parekh, and thank you, Professor Naik. And also thank you, Professor Venugopal, for such a wonderful presentation. So I'll be talking about, so can you all see the slide?
Yes, sir.
So I'm very thankful for inviting me. It is always a pleasure to talk about Ramanujan's work. And it's like talking about ocean from a pond actually. So Ramanujan is such a great mathematician and such a great, uh, so he had such great insight. So I do not know where to begin. So when Professor Paraki asked me to give a talk, so I was initially thinking what to talk about. And then I realized, okay, so Ramanujan knows infinity. Ramanujan knew infinity. Everyone knows, right? We have the book, the very nice book, very enjoyable to read, The Man Who Knew Infinity. And also there was a movie based on that, right? So he knew infinity. There is no doubt about that. And now the question is, how did he know the infinity? I mean, is there a way? So, for example, when he wrote letters to Hardy and Littlewood, they were busy settling questions about convergence of series. Convergence of series deals with infinity, right? So we have infinite sum. And Hardy and Littlewood, they were devising several inequalities with which they will show convergence of the series in question and such things. And then, so a letter reached him from a not so well-known Indian clerk who wrote about things Hardy couldn't believe himself. So you see, so he's writing down so many formulas. So they deal with summing series which are much more complicated than the general framework that they were uh, looking at. And also from the anecdotes, we know that we are certain that Ramanujan had a special way of dealing with infinity. So what is that? So from my childhood, so when I read about the book, The Man Who Knew Infinity, so I always wondered, how did he know infinity? What is the way? I mean, how did he? So knowing infinity means that the author means Ramanujan could sum these infinite series without any problem. So it was instantaneous for him. So he will take a series. So suppose he comes up with a series, he will just solve it. He will sum it instantaneously. So how did he do that? So then I always wondered how did he do that? Then I came to read about continued fractions. And also I came to know that in the first letter Ramanujan wrote to Hardy, he wrote about continued fractions. So he wrote quite a few theorems about continued fractions. And continued fractions are something that, so infinite continued fractions, those also deal with infinity. So I had so I thought maybe, so this is the way Ramanujan knew infinity. So I'll try to show why that is the case, why I feel like that. So before that, so this is the first letter. So this has become so famous now. So this is kept in museum in England. And so this is just one page from his first letter. So he wrote, I think, 5-6 pages, all with, so 2 pages for his introduction and several pages with these amazing formulas. I do not know if you can see. So these are really amazing formulas. So over here, so you see, so these are exactly continued fractions. So we'll be talking about these. What are continued fractions? And So these are all continued fractions. So some of these theorems were easy for Hardy, Littlewood, or their colleagues to prove. So, for example, 5 or 6. So soon they proved this. But several other theorems were really difficult for them to prove. So, for example, generalization of this. So this is known as Rogers-Ramanujan continued fractions. And these are not very easy to prove in the general settings. So before we go into that, so let us talk about this puzzle. So this happened in a winter afternoon in Cambridge. So P.C. Mahalanobis, so who is the person behind ISI Kolkata, he was a prominent statistician. So he was also in Cambridge during that time when Ramanujan was there working with Professor Hardy, and they were friends. So Mahalanobis often would visit Ramanujan, and they will chat about things. And Ramanujan, having his not so good health, most of the time will be sick, and Mahalanobis will keep him company, and they will discuss mathematics. Mahalanobis, being a statistician, also was a very good mathematician. So this is a puzzle that Mahalanobis read that day from the paper. So puzzle says that a man walked up a street with houses numbered 1, 2, 3 up to n. So numbers are consecutive. So man was walking down a street and he saw the numbers, house numbers are consecutive, and starting from 1 goes up to some uncertain number n, let's say. And he paused at the X door. So suppose there is a, so he took a pause at the X number door. And then he observed that the houses, the numbers, the house numbers to his left added up to the same number as to the house numbers to his right. So whatever the houses, so here the numbers will be 1, 2 up to x minus 1. And here numbers will be x plus 1 up to n. So we have 1 plus 2 plus up to x minus 1. This is same as this. And now the question is, just from this information, can you tell us what are x and n? And okay, so let us look at this puzzle. Let us understand what we are talking about. So over here we know, so this is just a arithmetic progression, and so is this. So we have two arithmetic progressions. We know how to sum them, right? So how do we sum this? Of course, we have the formula 1/2 the number of terms times the number plus 1, right? Or we can just employ what Gauss did. So you just write this backward. So you write this backward. So if you sum them up, it will always sum up to x. So x, and then how many terms are there? There are x minus 1 terms, right? There are x minus 1 terms. And then since we added the same progression backward, so we have to just divide by half. So this is the sum to the left. And to the right, we can apply the same procedure, right? So you take this and write backwards and then add them up. Then all the terms will add up to x plus n plus 1, right? So x plus n plus 1. And then how many terms are there? There are x minus n many, right? X minus n. N minus x many. So this is what we have. Now let us simplify this. So we have x squared minus x equals n square minus x square plus n minus x. And then we can simplify, and that gives us 2x square equals n square plus n. And from there, so let us multiply both sides by 4. So if you multiply both sides by 4, we have 2x square equals this, right? And that gives us 8x square equals 4n square plus 4n. And from there, suppose we add 1 to both sides. We have 4n square plus 4n plus 1 plus 1, right? So we added 1 to both sides. And if you simplify, so this becomes 2n plus 1 square. And this is 1 plus 2 times 2x square. So as a result, what we have is following. So we have 2n plus 1 square. So what we are trying to do, we are trying to solve the equations. We have to solve for n and x, right, to answer the puzzle. So we have this equals, excuse me, this minus 2 times 2x square, this is equal to 1. So we have to solve this. Now, this looks like an interesting situation, right? Interesting equation. So what mathematicians do, if they cannot proceed any further, what they do, they always generalize and try to see if something can be done for the general situation. So we generalize. Let us call this quantity, maybe not x, that will confuse us. So let us call this quantity a, 2n plus 1, and let us call the quantity 2x to be b. So we have this, right? We have to solve for a and b. That's what we have to do. Now, this is a class of equation. In general, we can deal with, say, d any number which is not a square, let's say. So if it is a square, then what you can do, you can take a minus square root of d times b times, you can factorize, right? And then you can argue that if a minus square root of d, suppose this is integer, then you can argue several ways. So if this is equal to 1, these two are integers, their product is 1, so each of them should be 1 or minus 1. And that way, you can do something over there. But we are more interested to know the situation when d is not a square. Precisely because our puzzle demands that, right? And these equations are called, it has come to be called as Pale's equations. And that is like so many things in mathematics. So things get attributed to people who do not have anything to do with them. As in this case, so Pale was a mathematician, not a very big name, but he did work on some, so he was contemporary of Euler, and he did work on some small stuffs. And so Euler was reading a compilation of results by Pale. So results were not by Pale, but the compilation was done by Pale. It was an editing work. And Euler, by mistake, attributed to Pale these families of equations. So that's how it came to known as Pale's equations. Actually, the equation goes back to long ago. So even Archimedes had, so there is a famous problem, it is called cattle problem, that can be derived, I mean, that can lead to so-called Pale's equations. But Archimedes, of course, never solved that. So the solutions to that question was not known, at least not all the solutions. It was actually Brahmagupta who gave all the solutions of these equations. And so D is not a square. And since then, this equation is known as Brahmagupta-Pales equation. So we'll just continue that name. Now, what did Brahmagupta do? Brahmagupta not only solved this, but he gave a very interesting approach to solve all such problems. All such families of problems. And his method, so-called circle method, Chakraval method, that's what Brahmagupta called, is very interesting. And recently it has once again gained some interest from the researchers, even after such long time. So after Brahmagupta, so these equations were, so Brahmagupta's technique was completely different. He used a very interesting technique, but we will not go into that. But then the equation was solved by several mathematicians. In particular, Lagrange gave a very nice solution to these equations using what is called continued fractions. So that will be our topic. So what are continued fractions? So in childhood, we have seen this kind of sums, right? 3 plus 1 over 2 plus 1 over 5 plus 1 over 7, let's say. We have seen. So this was probably, I don't know, like fourth grade, or I don't know, even before maybe. So, and so we used to call this staircase problems in Bengali. So that's why the name Ramanujan stairways to infinity. So these are continued fractions. So let us recall what happens. So this represents a number, and what is that number? Yeah, idea is that you go to the lowest step. So this is like a staircase, right? Go to the lowest step, work out this, and then use that for the previous step, and then use that for the previous step, and so on. So this is actually an algorithm. This is a number, but it actually represents an algorithm, right? It has a sort of, you have to work out the number. That's very interesting. So over here, this turns out to be 3 plus 1 over 2 plus, what is this, 35 plus 1, 36. So 7 over 36, is it? And this becomes whatever that is, 36 over 72 plus 7 maybe, right? Whatever that is, we know how to solve it. Now, why stop at only finitely many such? I mean, mathematicians, they always generalize, right? So they say, okay, so we have got finite staircases, right? Now we actually want to see how far we can go. So let us look at, say, infinite staircases like this. That's very interesting. Now, what does it? So we don't have the last step. So how do we sum this up? Now that's an interesting question. How do we really sum this up? What we'll do is following. So suppose this is x, and then you observe that x equals 1 plus 1 over whatever is at this place is again x, right? So x equals 1 plus 1 over x. Now if we simplify, so x square equals x plus 1, and that gives us x square minus x minus 1 is 0. So x equals 1 plus or minus 1 plus 4 divided by 2. So of course, x cannot be negative. We are summing up all positive numbers. So I'll discard the negative root. And if we discard the negative root, then we'll get x equals, from here, x equals 1 plus square root of 5 over 2. So this is a golden ratio, right? So that's very interesting. So we got a continued fraction that sums up to this very interesting and very well-known real number. Of course, there is a disclaimer attached to it. And that disclaimer is that, you see, we started saying that, okay, let this represent something. Now, how do you know that this actually represents something? So suppose this is not convergent. So in that case, naming this as X and then evaluating or performing arithmetic operations and then getting something could lead to contradictions, right? This need not be what this actually represents. There are those problems, of course. We have to make sense of convergence of infinite continued fractions and such things. But suppose we ignore that. Let us ignore the convergence. That will be just a little messy bit of mathematics. If we ignore that, then we have this very interesting bit of mathematics over here. So for example, so we have this very interesting continued fraction for square root of 2. Square root of 2 is 1 plus 1 over 2 plus 1 over and so on. Now this is very interesting. So probably we can prove this just like what we did over here and ignoring the convergence part. But then you may ask, how do you know? How did you guess this? So the answer to that is following. That is very easy. So you see, what all we have to do, first you have to guess very little about square root of 2. What is square root of 2? Surely this is more than 1, right? So it must be 1 plus some certain quantity x, some positive quantity x. Now, let us square both sides. So we have 2 equals 1 plus 2x plus x squared. And then that gives us x into x plus 2 equals 1. We subtract 1 from both sides. And that gives us x equals 1 over x plus 2. Now this is very interesting. So we have x equals 1 over x plus 2. So x is given in terms of itself. And we can exploit that. We can say that x equals 1 over 2 plus, now we write the same thing over again, 1 over 2 plus, we write the same thing. So first 1 over 2 plus x, and then we can continue. So 2 plus 1 over 2 plus 1 over 2 plus 1 over x, and so on. So x, we can continue this, and as a result, this portion will be our x. So you see, we know, so once we can guess little bit about square root of 2, we can find out the continued fraction for square root of 2. And this continued fraction will be very much useful for us. So let us see how. So first, let us look at what is this. So we cannot, so taking this to be our x and solving what is the continued fraction, like what we did over here, will just give us the answer backward. So if you do that, we'll get x equals square root of 2. And that will lead us nowhere, right? Because you see, square root of 2 is a symbol, and this is a symbol at best so far, right? So that leads us nowhere. Only, so it will be useful only if this extra bit of information over here gives us something more. And let us see, does it give us something more? So suppose we say that, okay, we cannot go till infinity and will not even attempt, but instead, let us go a few steps and let us see what happens. So let us say we go 2 steps, 1 over 1 plus 2. So 1 plus 1 over 2. What is that? This is 1.5. Let us go one more. So this is really off. We know, I think square root is 1.14 something, right? Square root of 2, something like that. So this is really way off. So let us look at the next one. So 1 plus 1 over 2 plus 1 over 2. Let us look at this guy. So this is 1 plus 1 over 5 over 2, right? So this is 1 plus 2 over 5. What is that? So this is 7 over 5. And how much is that? So that is 1.4. So it is decreasing, right? Let us 1.4 is that? Yeah, 1.4. Now let us do few more steps. Let us do, let's say, maybe these many steps. Let us see what happens. What is this? This is 1 plus 1 over 2 plus 1 over. Now can we just use a few work from here? Maybe not. Maybe just 2 plus, so this is 2 over 5, right? And what is this? This is 1 plus 1 over 2 plus 12, 5 over 12. Is that correct? And what is this? This is 1 plus 1 over 24 plus, so 29. So 12 over 29. So what is this? This is, okay, so 12 plus 29 over 29. And how much is that? That is 141 by 29. Is that correct? And let us see. So let us fire up our calculators and find out what this is. This is 1.413. 1.413. So, okay. So, oh, okay. So okay, I should have taken the next one. Okay. So here, so we have realized, so what is happening is following. So in the continued fractions, I should have done the next one. So you see, there are, so these, when you take odd number of steps, they converge, so they approximate square root of 2 from one direction, and when you take even number of steps, they converge from other direction. So I should have taken the next one, then it would have been better. But let us see what is square root of 2. So let's square this guy. Maybe I'm writing square root of 2 wrong. So let us square this guy and let's find out what this is. So yeah, so I squared this guy. Yes, precisely. So I was writing square root of 2 approximation quite incorrect. So if you square this coming out to be 1.9988 something. So this is quite close. So for all practical purpose, this is quite close. So this is completely wrong. This is, I think, 1.41. I wrote incorrect. So this is doing something. So our continued fraction for square root of 2 is giving us approximations of square root of 2 itself. That is expected because that's what we'll expect if this actually converges to square root of 2, right? So that is quite good. And you see, so this is a very useful technique. So here, let me answer one question that you might be having in your school. You might, you might have wondered in your school days. So why we used to write pi as 22 over 7, right? So pi is of course not rational, and we used to write this as 22 over 7. That is precisely because 22 over 7 was one such convergent in the one continued fraction of pi. So that gives us a very nice approximation to pi. I was thinking I'll derive this, but maybe that is for another talk. So let us proceed. So what are convergence? We just saw. So if we stop, so for an infinite continued fraction, if we stop after nth step, that's a rational number, provided all these are integer. This is a rational number. Let us call this Pn by Qn. These are called convergence. And these are called the nth convergent of the continued fraction. And if the continued fraction converges, so we say that the continued fraction converges to some real number alpha if these rational numbers converge to that alpha. That's what the convergence of continued fractions. So it will be a very nice exercise using the continued fraction. So you can maybe do experiment, find continued fractions of square root of 7 and write down the convergence. That will give you a very nice sequence of rational numbers which will converge to square root of 7. Now here is something very interesting that we have to learn before we talk about what Ramanujan did. So first is Lagrange's theorem. So Lagrange talks about continued fractions in this way. So this theorem says that a number x has a periodic continued fraction if and only if it satisfies an irreducible quadratic polynomial over Z. So what is a periodic continued fraction? A periodic continued fraction is a, so for example over here for square root of 2, so you see, so first two steps, 1 and 2, except these two. So this step was little unexpected from 1 to 2, but rest were all 2s, right? So it is just repeating itself. So similarly, so if you devise this notation for a continued fraction, say b0, b1, b2, and so on, this is for the infinite continued fraction that goes on like this. Then we'll say that the continued fraction is periodic if there is some, let's say, k, such that after this k, there is some, let's say, m, or maybe let us write this as k plus m plus 1, let's say, and such that this repeats. So rest, they just repeat this. Then we'll say that this is a periodic continued fraction with period m. So m is the period. And these are called the repeating pattern. So this pattern is repeating. These are called the repeating patterns. Now Lagrange's theorem says that a number has a periodic continued fraction if and only if it satisfies an irreducible quadratic polynomial over Z. So for example, square root of 2. This satisfies the quadratic polynomial x square minus 2 in here, right? And it is irreducible because x square minus 2 cannot be factored into linear factors, we know. Now, here is the result. So let d be a positive non-square integer. And so it's an integer which is not a square. And let Pn over Qn be the convergence of square root of d. And let n be the period of the continued fraction of square root of d. Then for any positive integer k, we have this interesting situation. So p kn minus 1. So we are looking at the kn minus 1 convergent. Kn minus 1 is convergent. And the rational number, the denominator and the numerator and the denominator of that satisfies this interesting equation. Now you see over here, we can compare this with our original equation, the equation by Brahmagupta and Pell, right? So a square minus 2 times b square equals 1. This is what we started out to solve the puzzle. And over here, so as a result, what we have to do, we have to look at the continued fractions of square root of 2, which we already know what it is, and then look at the convergence. Over here, you see, we want this side to be 1. So k times n, we want that to be even, so that this becomes 1. And what is the period? So period is of course 1 for square root of 2, because you see after the first two steps, it's always repeating the same 2. So as a result, we know that the period n equals 2. So as a result, we just have to look at k even to get solutions of the Brahmagupta-Pell equation. So for example, we had, so let us look at this one. 1 plus 1 over 2 plus 1 over 2 plus, we have to just be careful that we are looking at even number of steps. So what is this? This comes out to be 1 plus 1 over 2 plus 2 over 5. And this comes out to be 1 plus 5 over 12. And that comes out to be 17 over 12. Now, if you look at 17 and 12, and let us look at 17 square minus 2 times 12 square. Let us work this out. So I have my calculator ready over here. Let us calculate this. 17 times 17, that is 289. And then we have 2 times 12 square. 12 square is 144, right? And that gives us 288, and that is equal to 1. So we have found one solution of that puzzle, and we can take k any even number to come up with other solutions. So this was done. So this is not Ramanujan's work. This is very elementary. I think this was done by before Euler actually. Yeah. So this was done long ago, and even before that, Brahmagupta solved this using Chakraval method. Even before that, so here is what Ramanujan did. So Rogers Ramanujan continued fractions. So these are very interesting classes of functions. So here R of Q is defined to be this. Q, so Q is just a real parameter, let's say. Q to the 1/2 over Q plus 1 over Q square plus 1 and so on. So you see, we had that continued fraction, right? 1 plus 1 over 1 plus, which summed up till golden ratio, right? So this is just 1 plus Roger Ramanujan function evaluated at 1, right? If you take Q equals 1, that will give you precisely this portion. So it is 1 plus R of 1. And based on this RQ, there is another function that they define, that is S of Q, which is minus of R minus Q. These two functions, they pop up in number theory because of, due to very interesting problems, which goes back to Gauss actually. So regarding hypergeometric series, so one can write down continued fractions for hypergeometric series, and those are especially useful. And in that, so these functions occur. So these are very interesting. And what Ramanujan did was very interesting. So Ramanujan had this claim. So this is what he wrote to Hardy in his first letter. So, and this was proved by Watson soon after in small cases. So what he did is following. So he said that R e to the power n times pi, or maybe 2n times pi, or n times pi. Yeah. Sorry, square root of n times pi. So this is what he said, that these can be written down in exact form like this, apparently very easily. That's what he said. So this can be written down, can be exactly found if n be any positive rational quantity. So n could be rational even. And so he, of course, wrote the formulas, and it took the mathematicians long time to prove a few of them. And yeah, so these are even now they study this, and these are really hot topics of research. And so we do not have time to go over this. I wanted to make the talk for college kids, so I did not want to include uh, an introduction to this. Although derivation of these, at least in special cases, are very interesting. I would love to talk about that maybe later. So here are some continued fractions from Ramanujan's first letter. So here are, so he's writing this. So this is one way of writing continued fractions. So this is just 4 plus 1 over x plus, so this way. And so he wrote these continued fractions. These are very interesting. I mean, these formulas, there is no way to know how did he really came up with these formulas. So here are the, so the theorem 5, 6, 7. So these are, so he stated that it's very easy. And then he stated these as samples of the statements. And this is, of course, the first letter. I already showed this. And so here is the page from his notebook where he actually wrote down those results. So here are the, so you can see, so here are the continued fractions. So it would be, yeah, if we, so it was unfortunate that he succumbed to his fate. Otherwise, we would have known how to work with these even more, maybe. So Ramanujan was, so his method of working was completely different from other mathematicians of his time. So he is in some sense the last mathematician from following the legacy of Indian mathematicians like Brahmagupta. So Brahmagupta also, so in his famous Brahmasputa Siddhanta, he doesn't really describe how he came up with the Chakraval method and all those. So that is why. So they did not worry about the process, and they wanted to showcase the result, which was more important to them. And Ramanujan also. So he only after meeting with Hardy, when Hardy praised him for the demonstration of these formulas, then he wrote down proofs of a few of these. But probably he wanted to discover more than convince people that these are true. So it is always a wonder how he knew infinity. And my guess is that maybe through continued fractions, he had a feel of infinity. So thank you all for inviting me. And I hope you enjoyed the talk. So if you have any questions, please ask.
Sir, can you suggest some books on number theory so that the participants who are interested in number theory can refer?
Sure, absolutely, yes. So I like this David Barton. For elementary introduction, David Barton is very nice. Introduction to number theory. And for, so once you are familiar with this, then you can look at Niven and Zuckerman. It's also, so elementary number theory. This one is a very good book with all this historical. So this was So I actually became interested in mathematics after reading this book. So fortunately, this book came to my hand quite early in my school days. Although this book is not, not for school children. This is a higher level book only. But this is very interesting. This approach is very nice, and also a lot of historical anecdotes, and the author presents the book in a very nice way. I'm sure you will enjoy that book.
Thank you very much, sir.
And
Can I talk on it now?
wait. Camera கூப்பிடுறேன் acknowledgement பண்றேன். Science and mathematics.
Thank you all for organizing such a wonderful event. I hope, presenting in front of kids would have been much better. It's always refreshing to see the kids enjoying what you talk about. But at the present scenario, so we have this COVID menace, but we have to still continue our activities. It's very commendable that you came up with such nice program.
Okay. Hello, Madri sir. It is very nice talk by you, and we learned lots about continued products. And thank you very much. Within short period of time, you agreed to give the talk, and you are very cooperative with us. Thank you very much. Thank you all the participants. Nice to see you on the chat box. And we are very sorry, in the beginning there was no sound and a little bit echo because of some technical issue. But afterwards it went well. And thank you, because of all of you. It is the great success of our Sky Minds web series. I have posted the feedback link on the chat box. So please fill the feedback and submit it. You will get the certificate soon. Thank you, one and all.
Thank you, ma'am.
Thank you.
Thank you.
So I'll sign off.
Live will close. Live. YouTube live. Camera put on. YouTube live will close.
Mashira, link, I have put the link, no? So let them feel, no? Okay. 5 minutes. The link is on the YouTube itself. 5 minutes.
They got the link, no? Just check your WhatsApp chat.